Good afternoon, everyone. So yeah, my name's Bulgin. I work at the University of Reading. I'm also part of the National Centre for Earth Observation, and I don't normally sound like this. So I'm going to apologise now for the squeakiness. Those of you at the back, can you hear me? If you can't, start waving frantically, and we'll get an interpreter to come and help or something. Okay. So anyway, I'm going to talk to you today about uncertainties in thermal remote sensing data sets. Because you've all been sitting here for quite some time listening hard, we're actually going to start with a quiz. So there's a bit of audience interaction. Okay, so I'm hoping this is going to work. Right, if you get out your mobile phones or your laptops, and if you go to slido.com and you put this number in, you will have access to the quiz. And you should be able to answer this question here. So I just want to get a feeling for how important you think it is to have a measure of confidence in the data that you're using, okay? Just going to say your responses are entirely anonymous unless you find them out. So if everyone votes, we can see what the feeling is in the room. Please be honest. Okay, I imagine most people have voted by now. So it's fine if you keep sending in your answers. I'm pretty glad that nobody said it's not important. I'm actually quite pleased that extremely important won out. I wasn't sure if it was going to. I think there are cases where people take data sets, they think the uncertainties are reasonably important, and if the information is there, they'll use it. But if not, they'll still use the data anyway. Okay, next question. So you should now be able to see the next question on your Slido. Do the terms error and uncertainty mean the same thing? Okay, I take it most of you've answered now. So, you are right. So, spoiler alert, no, they don't mean the same thing, but they are very often used interchangeably, which is why I asked that question. So, thank you for the honesty of the 11% who said, I'm not sure, because I think probably before I started working in this area, I'd have said the same thing. So, final slide question coming up now. Given that we now know they have different definitions, which is this the definition of? So yes, the majority are right in this case. It is the definition of error. And I think sometimes it's easier to tell the difference between them when we start to write it down. Right, well, thank you for indulging me and taking part in the Slido. Now you've got to listen to me squeak for a bit. So, every measurement that we make whether it's in situ, whether it's remotely sensed, is going to deviate from the true surface temperature. And that's because we have imperfections in the instrumentation that we're using and also in the measurement process that we're employing. So really, in order to use data correctly, and this is something I'm going to try and convince you of in the next 15 minutes or so, you must consider the uncertainty in the measurement. So error and uncertainty are two different concepts. So the error is how different is the measurement from the true value. And the uncertainty is the degree to which that measured value is in doubt. Now, typically, we don't know the measurement error. If we did, we would just correct for it, and we give you perfect measurements of surface temperature. Everyone go home happy. But because we don't know it, what we provide instead is an uncertainty, and that is basically a measure of the dispersion of a possible distribution of errors associated with that measurement. Right, we're now going to have a look at a practical example, and I'm going to try and show you why uncertainty information is so important. So imagine we have a research question. We're looking at Africa, and that area that I've highlighted over the Sahara, we want to know what the diurnal cycle is in this part of the African continent over a given day. So we've got some data, entirely made up, but plausible. On this graph, you've got on the y-axis, you've got the temperature, so 280 Kelvin going up to 320 Kelvin, and then we've got 1 day's worth of data along the x-axis. And so I've extracted the time series, and we can see that there's a nice low temperatures, a peak towards the middle of the day, and then it cools off again, as we might expect. So we want to answer our question. So we can identify the maximum temperature, and we've plotted Tmax, this is maximum temperature here. We've identified our minimum temperature, and we've plotted Tmin here. And then we can say, okay, well, the difference between our Tmax and our Tmin, that must be our diurnal range. That's the answer to the question. Or is it? The one problem with what we've just done here is that we've assumed that our measurements are perfect. What my time series really looks like is this. So now I have the same observations. I have a measure of uncertainty associated with each one, because in size, depending on the observation. Now, when I superimpose my Tmax and my Tmin back on here, and I look at this observation, and I think, okay, perhaps the assumption I made before wasn't such a good one, because there's a massive uncertainty on that particular observation. And perhaps actually my Tmax is quite a bit larger than I thought it was, which means my diurnal range might be larger, or actually it might be quite a bit smaller, and in which case my diurnal range will be smaller. And what I do with that information is going to be dependent on how I want to use the data and how important it is to know what this possible range might be. What I'm trying to illustrate is that the uncertainty information is really key for understanding just how sure we are about the values in the data. Okay, so I'm going to spend my screen, I'm not going to talk it at all, telling you about how we generate uncertainty budgets. So the approach that I'm going to present is something that we do as part of the European Space Agency Climate Change Initiative that Mike just introduced really nicely. We use a bottom-up approach, and we use the principles of metrology, which is the science of measurement, and we apply it to sea surface temperature products and land surface temperature products. So essentially, a full uncertainty budget is the sum in quadrature, because that's how you sum uncertainties, of the uncertainty that we can estimate from each source of error in our measurement. So if we take a bottom-up approach, we can construct an uncertainty budget by first writing down all the possible error sources, and we sometimes refer to these as error effects. So there's a few questions that we're going to ask as we undertake this process. So one of the questions might be, are there any possible sources of error in the way that the instrument is making the measurement works? Is there any possibility that it's not completely calibrated, for example? Is it noisy? Can it measure things perfectly? And then typically, you've had talks on how we go from the radiances from a satellite through to a surface temperature. We're not using that raw measurement of radiance, we're doing something with it. And we might introduce more sources of error by doing that. So perhaps we'll use some auxiliary data that might have an associated uncertainty with it that we need to account for. Perhaps we're using some coefficients or parameterizations. How confident are we that these are the right things and the exact numbers? And is there any kind of pre or post processing of the data that we're doing as well, which we might not get entirely right? So I want to give you an example of how we're going to construct an uncertainty project. And essentially what we do is we go from the measurement equation. Okay, I'm not going to go into massive detail about how this particular land surface temperature retrieval works, but I'm using it as an example to show how we set up the process, okay? So in this equation, we've got land surface temperature, that's LST, and then we've got a whole load of things that it's a function of. So the first thing that it's a function of is some brightness temperatures. So these are the T terms, 11 and 12, and 11 and 12 micron channels, okay? So we've got these T terms, and then we've got a handful of coefficients, A, B, and C, and they have dependencies on things which don't matter too much at this point in time. And so what we do is we separate those out so we can think about them independently. So here we have what we just call an observation vector. It essentially just contains all the observations. So that's T11, T12 there. And then we have this beta term, and that is just a collection of all of our coefficients. So that contains A, B, and C. And then the astute among you will notice there's this weird +0 at the end of our equation, which isn't really normal when you're doing a retrieval. But in uncertainty world, that is going to capture the uncertainties that are not associated either with the terms in the observation vector or in the terms in the beta vector. And I will explain in a minute what sort of things fall under that +0. Okay, so this looks a bit scary and complicated, but we can construct tables that list all of these possible sources of error, essentially. So we've got 3 different sections here. Uncertainties associated with the retrieval parameters, so that's a beta. Uncertainties associated with the observations, that's our y. And then uncertainties associated with the retrieval process. So this is our +0 term. So if we just zoom in on one of these, this is the uncertainties associated with retrieval parameters. We have beta here. Remember, we have coefficients A, B, and C. And then for each one, we can literally go in and say, okay, associated with coefficient A, there are 3 different possible sources of error. And in this case, it's basically what that coefficient was dependent on. So the fraction of vegetation, there's a fitting error, and a precipitable water error. I'm going to talk about this a little bit in a minute, but we can try and say something about the correlation length scale of that error. We can say how we might attribute it, and then we can say how we calculate the sensitivity. So you can either directly differentiate the retrieval equation and get it that way. If you can't do that, you might construct a simple model for that uncertainty. It might be that you can't do it at all. Some of these are not attributed. I'll come back to that as well. And then this mysterious +0 term, which I promised to explain, contains all the things that happen as part of the retrieval, but they're not directly connected to a specific term. So things like geolocation. Are we really looking at the bit of the Earth that we think we're looking at? Cloud detection, this is a big one. When we talk about this, Liz is laughing at me. When we talk about this in more detail towards the end of the presentation. But essentially, we're going to retrieve the surface temperature and we're going to do it with infrared data. We've first got to work out if there's cloud there. And if there's cloud there, we need to throw that data away. Because otherwise what we retrieve is either the temperature at the top of the cloud or in part the temperature at the top of the cloud. And then people get very unhappy. They want to look at long-term temperature change and it's just for the clouds. So got to be careful about that. And then we also use a transfer model and some weather prediction data. So they fall under here as well. And so we build up our uncertainty estimate. So we start with our satellite measurement at the top, sat level 1 data, and that has some error effects associated with it from which we calculate the uncertainty. And then we propagate that through into level 2. That's where we're doing the retrieval. That's where we are calculating the surface temperature and the instrument is looking at. But we need to be aware that when we do that, we introduce some other sources of uncertainty because we're doing a retrieval process. And then perhaps you want to take that data and grid it, put it on a regular lat-long grid. Users tend to prefer that. But in the process of doing that, we need to propagate the uncertainties now and again and add any new uncertainties we're introducing when we're gridding the data. And then finally, if you want to make multi-product surface temperature products, then you need to propagate your uncertainties downwards and add uncertainties that are coming from things like interpolation. Okay, so what do we do with all this information? What do we actually give to the data user? Well, what we do is we take each of the uncertainty estimates and each of the error effects, and then we group them into categories, essentially. So we group them depending on their correlation length scale. So you can have uncertainties that are independent. That means that the uncertainty in this pixel is completely unconnected to the uncertainty in a neighboring pixel. So an example is instrument noise. The instrument noise in this pixel is not related to the instrument noise in a neighboring pixel, so that would be independent. We have systematic. These are uncertainties that are correlated over a specific scale. So we do our retrievals through the atmosphere. So typically we have some uncertainties that arise because we are doing a retrieval through the atmosphere, and therefore they're correlating over atmospheric length scales. So that's an example of systematic. And then you have common. These are uncertainties that are common to all of the observations that you're providing. So a good example of this would be a calibration uncertainty that is relevant for all of the observations from a particular sensor, for example. And so we collect them up into these categories, we add them up in quadrature, and then we provide this breakdown of independent, systematic, and common, as well as a total uncertainty. It's worth noting that you can have more than one component in a systematic. If you have two particular correlation length scales that are different, over which you have a collection of uncertainties. So I gave you the atmosphere example. The other one might be the surface when we think about surface temperature. So perhaps what you're assuming for the emissivity might have a different correlation length scale to the atmosphere. The question you're all asking, I hope, is why on earth are we doing this? I think it's a good question. But the main reason is to make it possible for you to have the most full use of the data that we're providing. Typically, users will take our data and they'll do something with it. They won't just use it as it is. So they might calculate coarser resolution data because they want to compare to climate models. That's a great idea. But we need to be able to propagate the uncertainty so we know how confident we are in that end value that we're comparing to the climate model. Or we might want to take regional averages. And to correctly propagate the uncertainty, you use a slightly different equation depending on the correlation length scale. And that's why we provide those three different components. So just to give you an example, this is a land surface temperature example. So we've got land surface temperature here, top left. This is the random or independent component. We've got two forms of systematic uncertainty. So an atmosphere one here, and a surface one related to surface over there on the right-hand side. And you can see these are quite different. So the atmospheric uncertainty has quite a much lower correlation length scale than the surface one that's related to changes in volume. Okay, and just to finish up, what about the things that we don't know about? I alluded to this earlier. So cloud detection is a really good example of something we can't yet quantify the uncertainty in. It's probably quite important. So if we think about the case where we have level 2 data, so that's where we originally do our retrieval on the grid that the sensor is seeing. If we have a pixel that has a cloud in it, and our cloud detection has failed, and we say it's clear sky, then the uncertainty due to cloud contamination is going to be massive. It could be of order 10, 20 Kelvin if it's cold cloud. And that isn't currently in because we don't know how, we don't know it's applicable. Because if you think about the neighbouring pixel, when we got it all right, and it definitely is clear sky, then our uncertainty due to cloud contamination is 0. So if we gave you that observation and said, well, it might have a 20 Kelvin uncertainty, you'd probably get quite upset and not use any of our data. So it's a really, really tricky problem. Most people don't actually use the data at this level. They actually use Corson data. And it's probably not quite as bad when we get to this stage, she says, hopefully. Generally, it's a small subset of the data where we've got the cloud detection wrong. So when you Corson it and regularly grid it, then you're going to have a small number of observations where you might have a bit of cloud contamination. And the process of averaging out the land surface temperature will reduce that uncertainty. And it is still there. So what I'm trying to say is this is a work in progress. This is still an active research question. And there are still things that we can do in this area. Okay, so in summary, error and uncertainty do not mean the same thing. So please be careful when using these terms. Uncertainty information, I would say, is essential for making good use of the data, particularly when you want to use it in a decision-making context. Because you need to know how good that data is, how well it represents the thing, the question that you're asking. When retrieving sea land surface temperature as part of the CCI project or program, we use this bottom-up approach with metrology. We try to understand all our possible error sources and propagate them through our retrieval. And then we provide this breakdown of uncertainties by correlation length scale so that you can propagate the uncertainty further into your derived products. But there are still many unknowns, and this is a work in progress. And thank you very much for putting up my voice for that long.
On systems such as the Terra platform, you have the ASTA data, which is obtained sporadically with MODIS data. Doesn't that allow you to develop, for example, machine learning methods for detecting subpixel clouds?
I was very tempted just to apply any other kind of nothing without the mic. So theory, yes, you could try and use high resolution data to understand something about the coarser resolution data when you have both at the same time. It's not necessarily quite so useful when you don't. I mean, it's another way of trying to detect cloud. There's a whole history of methods. So we kind of started off basic thresholds on data. We got a bit more sophisticated by using kind of Bayesian probabilistic approaches. Machine learning is another one, which tends to have quite good results, but it is dependent on having good training data. So it's only as good as the regions that you can train it on. So it is likely it will still struggle in regions like snow-covered surfaces. It's quite difficult to differentiate, like low-level fog, for example, over the ocean, which is warm. It's warm and dark. The ocean surface is warm and dark. So there are cases where even machine learning methods will struggle, but it is one approach you can take.